More people might come funneling in, but I'll go ahead and get started now. So, hi guys. Um, so my name is Victor, and I'm joined by Manuel, and we're both going to be explaining some of the main topics you guys are going to need to know for the exam one review coming up in operating system, or coming up on your first operating systems exam. So, the main agenda that we have for today, and the main things we're going to cover forking, we're going to cover threading, specifically threading using p threads, and we're going to cover some calculations that are going to show up on the exam. And to start off, we're going to go ahead and show a demonstration of forking, what you may see on the exam, and yeah. And if there's any issues or anything, just let me know. But um, Manuel, if you want to just go ahead and get them started on all the forking stuff, that'd be great.
Yeah, let me just share my screen real quick. Let's see. Okay, there you go. Just share my screen. There you go. All right. All right, guys. Welcome to the exam review session. Today we'll be talking about forks, right? So for during the exam, you'll have an extra credit opportunity that'll be mainly dealt with forks, and also this will also be brought up in the exam. So the fork system call is basically just allows us to create a new process by duplicating the calling process, which just basically means we can call a new child process. Right. So during the extra credit and exam, right, Professor Rincon will just leave you like with the output statements, right? And it's our job to print out the output that he wants. So if we go back to, oops, it's kind of hard sharing my screen. Right. So let's say he wants grandchild process one and four grandchild processes for child process three. Right. So first, right, we're gonna get the cout statement here. Right. So if we want to create an amount of child processes, right? So let's say we want four. Right, we're gonna iterate through and create four processes, right? But right, in order to create child processes, we need to call fork, right? So if fork to zero, right? This is true. Then we're just gonna say I'm a child process. There you go. Right, but this, right? You can just basically call it here and say, oh look, you already created child process, right? But we try to build this and run it. Let's see. Right, here you go. Right, we get our child processes, but they're out of order. Right. So for every time you call fork, you call exit. Right. That terminates the process. Right. But that's not it. Right. If we just do this itself, right? Let's see. There you go. We do this ourselves, right? We might get the correct output. Let's see. There you go. But see, we get input. So for every time you call fork, you call an exit, which allows us to terminate the process. Right. And we're gonna call wait, which will just make sure that we're going to output correctly. We always get the correct output no matter what. So if we build here, there you go, and then there you go, right? But let's say we want to create a grandchild, right? Oops, there you go. Let's say we want to create a grandchild. So let's say if I is equal to zero, right? Then we're going to create a child process, a grandchild process, sorry, right? So if it's this I is equal to zero, right? We're going to call fork again, right? If this is true, then we're just going to say, oops, right? A grandchild process from the child process. There you go. Right, and you call an exit after the fork and a wait to make sure it's printed in order. So you notice we have two exits and two waits. A key rule to remember for every time you call fork, right, that's how many exits and waits you should have. So since we called two forks here, we should have exactly two exits and two waits. Right, so if we try to run it now, let's see, we just save it. If we run it, there you go, right, we created a grandchild process, right? Let's go with another example, right? Let's see. Here you go. Oops, sorry. Let's go with, well, let's say if child process 3 has 4 grandchildren, right? We can't output that 4 times, right? So what we're going to do is if I is equal to 3, right? We're going to go up to, right? We're going to iterate again, right? The j is less than 4, right? We're going to increment, and we're going to call our fork, the fork system call. If this is true, right? And this is going to say, oops, let me just copy this here. I'm a grandchild process. Here you go, right? Remember, we called another fork. So at the end of this output statement, this exit to terminate the process, and then a wait, no pointer, at the end of the for loop to make sure we get the correct output, right? And then this should allow us to, let's see, there you go. Right? We created multiple grandchildren for child process 3. Does anyone have any questions or are confused anywhere? No questions? All right. Well, there's no questions, or you guys feel confident? You want me to do another example? Right. At most, this is probably like how easy the extra credit should be. Right. Exam shouldn't be no more like no difficult than this. So, right. So, would you guys like me to do another example, or you guys feel confident?
I'd like to see another example.
Okay. All right. So let's say, right, okay. Here you go. Let's say we have this, right? We create the parent, the child. Let's see, child 1, child 0. Let's say it's a child 1, grandchild 1, grandchild 2, grandchild 1, right? Child 2, child. Let's see. Yeah, child 3, grandchild 3, and grandchild 3. Here you go. Right. Let's say we have this. Right. Let's say we want to output this. Right. So, right, we can reuse this most of the code here. Right. I'm sorry. Right. Let's say, hold on. Let me just put most of this here. Oops. Okay. There you go. Right. So this here. Okay. There you go. And here you go. All right. Right. So do you guys understand this? Right. We're creating a child process. Right. We want to print how many child processes we need. We call fork to make sure we're creating new child processes. Right. So let's say you want to do this example. Right. Well, you can use an if and for loop statements. Right. Like you can hard code this. Right. Right. You don't know the solution, right? You can hard code this, right? But there is another easier way. Right? So let's say, hold on. Exit 0 and wait, no pointer. Here you go. Right, so let's work. Okay, here you go. So let's say if I is equal to 1 or I is equal to 3, right? Then what we're going to do is, right, we're going to want, let's see, we want 3, let's see, 2 grandchild processes, sorry. So we 2, 4, right, J, right? We're going to create a grandchild process. J is less than 2, A plus plus, right? If, right, if we call fork, this returns true, then we're going to create grandchild processes. Right, then we just get the output statement from here. Oops, sorry. There you go. All right, right. Remember, right, we're done here. We're not creating any more child processes, so we call an exit. Right, and then outside the for loop, we just call wait. Wait, no pointer. Right, so we got to make sure that we got everything correctly. Right, we called 2 forks, so we exactly have 2 exits and 2 wait no pointers. Right, so let's see if this builds correctly. And let's see. There you go. Right. This is something you could expect, like extra credit wise, most difficult problem you'll probably see. Like it won't be no more than this. Maybe up to like 4 like 4 grandchild processes, but that's it. Right? You won't get any grandchild process or great grandchild. Right? So don't expect like anything too difficult. Does anyone have any questions or let me clarify some things? Oh, sorry. Oops, I didn't see the.
No, I think he explicitly states that if you do the hard code solution, it's like 0 points.
Is it? No, like
Yeah.
you can hard. Actually?
No, I mean like if you were to just like type like I think.
Oh
he
yeah,
says
oh yeah,
0
yeah,
points.
yeah, yeah. Oh yeah, if you type it then yeah, if you just say there's like output it like this in there, like in Moodle, then yeah, you'll get no points. Like you won't count anything. Sorry, I can't see the chat, so let me just get on my phone real quick. Let's see. Oops, sorry. All right. Oh, okay.
Oh
Okay.
yeah,
So
yeah,
like,
yeah. No, you can do multiple if statements. That's fine. The
yeah, you
codified
can do
if
multiple if.
statements.
Yeah, you can do you can do multiple if statements, right? But like if you're running out of time and you can't think of it this way, right? Like the most like the Professor Renko would say, like, oh yeah, you could have done it this way, but you guys should be fine.
The most important part is that as long as you're using the fork function and you're using the conditionals and the exits and the waits and stuff, then you're all good.
Yeah. Does anyone else have any questions or want to see like an example, like an example, like from an exam, right? Or like something they might see in an exam. This shouldn't be like this is probably like the most difficult he went, but it shouldn't be too. Like it shouldn't be as bad. It's a, I don't know if you guys don't want to or
Yeah, it'll be like the exact same pattern of the exam.
yeah,
Like expect something like that. It might be like less parent, less grandchild, but like it's like the same idea.
yeah. Right, like you're not gonna deal with like great grandchild or like your great grandchild. Like he won't go past that. Right, and he won't go past like like let's see here, child 4. Right, he won't go past that. Like anything more than like he won't go beyond this. Like that's where he won't go beyond.
I have a question.
Yeah, go ahead.
If we're taking OS with Paris, can we expect to see stuff like this too?
Don't know. I never took him for OS with Paris.
Does
So
Paris use Moodle as well for all of his assignments and everything? Or does he do like in paper stuff? I haven't taken him either, but if he does
yeah,
everything on Moodle, I'd expect it to be similar.
Like the exams are, he calls them quizzes, and part of it's multiple choice and part of it's like pre-response. He said.
Okay, that's.
okay.
I'd imagine it would
Huh?
be pretty similar, but I
Yeah,
can't say for sure.
Yeah, we're not. You can't guarantee because we never took Paris for operating systems. But I mean, it should
All
be
right, no worries.
somewhat similar.
Thanks.
But yeah, does anyone else have any more questions or want to do another example? Are you guys lost in anything? And okay. Think there's no questions here, so I guess we can move on to the next topic. So I'll pass it on back to you, Victor.
Okay, let me go ahead and bring up the slides again. So now that we finished forking, next thing that we're going to be doing is we are going to be doing threading. So whenever you get a threading problem, first thing you should always do is read the problem, make sure you have a pretty good idea of what's going on. So we have this, or basically what's going to happen is you are going to get some kind of input like this or some kind of question like this. So input will be given an integer value n representing the number of ASCII values followed by n integers representing ASCII values, given the following input 867, etc., etc. So on the exams, you're basically going to automatically get these inputs taken in by default. There's going to be methods and functions there to do this by default. And basically, you're going to be given some kind of input and you're going to be told to do some kind of evaluation on this input and then give some kind of output. So I'll go ahead and show what the code for that's actually going to look like. So just so you guys know, whenever you get the problem, initially, you're going to get some stuff by default. So you'll get everything you need to basically take in the input by default. You'll probably get some basic like conditionals or like basic structure of the code, but then you'll be asked to fill in like certain parts. So like you might get this if statement, you might get this error creating thread stuff. Really, there's only a few things that he's looking for on these questions. He wants to know, do you know how to do a pthread create? Do you know how to do the pthread join afterwards? Do you know how to basically create the dynamic arrays? And do you know how to append these values? And then the last thing that it's going to be looking for is, do you know how to actually work on the void pointer function? So we'll go through each of these one by one. So first off, and you probably won't be asked to do this on the exam, but the first thing you may be asked to do is dynamically allocate arrays for thread IDs, argument structs, and character arrays. And because we're dealing with threads, this is something we kind of have to do. So again, this is probably something that you're going to get, but there's three things that you're going to need. So you need something to keep track of your pthread IDs. And this pthread underscore t, this is just the built-in pthread.h with C++. Um, and like if you notice, basically all of these are set up the same. We have a dynamic array to hold our arguments, a dynamic array to hold the characters that we're going to need for our output, and the dynamic array to hold our pthread IDs, which will be useful for the joins later and also when we're doing the create. And you'll also be asked to do this. So in this question specifically, you're given these initial two parts, but you're not given the second part. So you're not given how to actually initialize them. So arg_i.ascii value, this is pretty simple. If you want to figure out what values to put in here, simply go up to the arguments and then you get a pretty good idea. So in this problem, we're given the ASCII values up here. And all we really have to do is just add the values that we have in this function into this dynamic argument array. And that's really all there is to it. Like, this is pretty simple. And the reason we have the reference to charray is because in the argument structure, this is also a pointer as well. But getting it into this is pretty simple. Just look at the struct and then just append the values that you have up here, and then you're pretty much good. This part is pretty simple. The next thing is you need to know how to do pthread create. So the way you do pthread create, and this is pretty much always going to be the same, like this is never going to change. You run your if conditional, you run pthread create, you get a reference to your thread ID. We have no restrictions or anything, so we just put null pointer here. We put in our third call is always going to be the function or argument that we're calling, and this is the ASCII touch up here, which we'll get into in a second. And then we also want to take in our argument as well. And this is basically always going to be the same. You might be asked to like this arg variable might be named something else, but or this routine might be named something else, but this is pretty much always going to be the same. And then you run not equal to 0, and if it hits, there should be error handling stuff here, but as long as you know how to do this pthread create, you're pretty much set. So with this pthread create, there's a specific call to this ASCII touch function, which is up here. So I'll go through step by step. So you'll probably get something like this: struct arguments, arg pointer, and then you'll be asked to fill in everything else that comes with it. So if Rincon should have mentioned this at some point, but the reason that these take in void pointers as arguments is that they're very generic and they can basically take in any arguments. So the first thing that we need to do is we want to take our void pointer and we want to cast it to whatever the type is that we're trying to work with, which in this case is the struct arguments pointer type, which we know because the struct is right here and this is given to us as well. So casting here is pretty simple. We just type in struct arguments pointer of void pointer, and that's going to transform this void pointer, which if we go back, we remember is this guy right here, this arg_i, which is basically our ASCII value and our ASCII char pointer. So basically what we've done is we've created a new thread, which is going to this ASCII touch, and it's taking the inputs, which is our ASCII value and our ASCII char pointer, and it's turning it into this argument that we can use in this function. So hopefully that makes sense. And since for this question specifically, we're doing a char casting, this is unique to the problem, so you may not be asked to do this specifically on the test. But this problem asks us to do character casting. So we dereference the arg pointer of our ASCII char pointer. And the reason we have this dereference is, remember, our ASCII char pointer is a pointer, it's not a value. So we actually want to adjust the value here instead. And we want to adjust that to be the character value of whatever our ASCII value is. So again, we just get our arg pointer ASCII value, and that's basically all we do. And now our ASCII char pointer, the actual value of it, is going to be assigned the actual character that we need it to have. So hopefully that makes sense. And on any question like this, any routine like this, any void function, you're always going to return a null pointer. This will always be the same. So these first and second lines are always going to be the same. This second line may vary a little bit, but this is like the basic idea. You have your arguments, you make sure you cast the void pointer, you dereference any values you need, make any changes you need to it, and then you return the null pointer. And that's literally everything we need for pthread create. And then the last thing that we need to do after this is we need to join our threads. So to join our threads, this part's pretty simple. This is probably the simplest part of everything, but we simply run through a loop of whatever the input size is, and then we run pthread join in there. And the only thing we need for pthread join is the actual location of, or the actual thread ID at that position, and then the null pointer. And this is very important. I think, if I remember right, it's important for synchronization purposes and making sure everything finishes in time. And I think this is worth 10 points on the coding section. The pthread create is 15, and then everything else I think is like another 15 or something like that. It's been a while since I've taken a class, so but this is important. This is a super easy function to get. So just remember, on pthread join, all you need is this TID at position I and then null pointer, and you just loop through it. It's super simple. And then for the final cout, all we have to do is give the input that we're looking for, and then our character array. Remember, our character array, we adjusted it in this function. And because of our threading, we were able to go through every single character. And every single value we have at the ASCII char pointer is going to be an actual character that we're looking for. So if we go back down, we just put in whatever our character array is, which is going to be the actual word that we're looking to make. So I can go ahead and run this. Should have everything we need here. And let me pull my terminal. If it feels like loading. Okay. And we'll just try this just to show. So sorry, guys. Okay. And then normally you're going to just get this input in by default, but because I don't have that set up, I'm just going to put it in manually. So we have a size of 8. Our values are 67, 79, 83, 67, 51, 51, 54, and 48. And this is our final value. So given the ASCII values from the input, the word is COSC 3360. So we've basically taken these characters, utilizing multi-threading, we've basically managed to synchronously alter all of these into their corresponding character values. And that's pretty much it. But yeah, remember how to assign these specific arguments. Remember what these dynamic arrays are for. Remember how to do the pthread create. Remember we need the reference to the thread ID, null pointer, the routine that we're calling, and then the reference to wherever we're holding our arguments. And remember how to do the join. It's just give the thread ID at that position, comma null pointer, loop through the size, and then for the void function, the routine, remember to cast our void pointer to whatever type we're working with. Remember to dereference any values that we're working with however we need to. And always remember to return null pointer on these. And then on the cout, we just return whatever our character array is. This is our final output. And yeah, that's it. Hopefully I explained that pretty well. If anybody has any questions, go for it.
I think something also to add, right, is I think if you correctly call pthread create and pthread join, right, but you're unable to create the void pointer function correctly, right, you'll still be able to get points, right? You'll still be able to get points, right? Because during the exam, if your program does not compile, then you'll get no points.
And yeah,
Right, but
I can explain what each pointer is for. But yeah, Manuel's right. As long as you have something that's like semi-functional, you're going to get some points. Like it's very easy to get partial credits. Rencon's pretty lenient with this stuff. But okay, what each pointer is for. Okay, I'll go through one by one. Sorry, my virtual machine's being very slow. Okay, so this int pointer ASCII values, this is essentially just here to store the input. So remember, we have 67, 79, 33, 67. This is here to store the input. How necessary this, I guess this pointer is somewhat necessary. I'll explain here in a second why. But the dynamic allocation, so pthread pointer TID, we need to be able to reference the TID, and that's basically why we have that. The struct arguments we need to be able to reference. A lot of this is just because we're passing by reference into our routine. So remember, we have this void pointer. So whenever we're passing in an argument, we have to make sure we're passing in the pointer of that argument. And then the char pointer char array, I guess you could have, instead of the pointer, you could have just char normally. But you pretty much always want to be working with pointers whenever you're doing anything that involves anything multi-threaded, just to make sure that everything's getting put in the same location. This one specifically, so arg_i.ascii value equals ASCII values at I. So remember earlier, we have the int pointer ASCII values equals new int size, and then we append the actual ASCII values. And because our struct from above doesn't require a pointer or anything, we don't actually need to take the reference of this. And then for the ASCII char pointer, because our structure above asks for a pointer, we have to take in the reference of the position of the character array. So it assigns the address in the character array, basically. And then in the create thread, we need to take the reference of the TID, and this is super important because you need the reference of the thread ID, because when you're doing multi-threading, you need to know exactly where in memory your thread is going to be. And for the arg, remember we're doing a void pointer ASCII function, or we're doing a void pointer function, so we need to be able to pass in the reference of our argument. And yeah, that's basically it. Hopefully that explained it okay. And yeah, go ahead and bring everything back up. A null pointer.
yeah. Has anyone got any questions so far? Review over anything?
And the last thing we're going to be going over is the calculations. So give me just 1 second. So let me just pull something up really quick. Okay, so we'll go ahead and get started on this next part. So calculation questions. I'll go ahead and start us off. So calculate the following parameters for this hypothetical computer system with the given features. So A, we're in octal notation. So that means base 8. IR equals OP code plus memory address. IR is equal to 12 bits. PC is equal to 3 octal digits. And memory word size equals IR. So how do we solve this, right? So there's a few things we should know at first. So to calculate the number of different OP codes, there's a few things we need to remember. So one, our IR is 12 bits. And we know that the memory address must fit within the memory size, which is 3 octal digits. An octal digit is 2 to the power of 3, or 3 bits total. So for 3 bits, we have uh, 3 total bits. And because we have 3 of these octal digits, that means we're doing 3 bits times the 3 octal digits that we have, which is equal to 9. So that means that the memory address here is 9 bits. Therefore, the remaining 12-bit IR is used for the opcode. So that means our opcode is 12 minus 9 equals 3 bits. So it'll probably be easier if I do this on like a whiteboard. It'll probably make the explanation a little bit clearer. So I'm going to try that and see if I can do it. Give me a second. Okay. I pulled up the whiteboard. If you guys aren't able to see it, I'll just pull up the slides again, but either way is fine. Okay, give me just a second, guys. Um, give me just 1 sec. All right, let me go ahead and put this in. Okay, that's super small. I don't know why that's so small. Oh, it's so blurry too. Yeah, let me see if I can just get the text. I don't even think I can get the text. Sorry about this. Give me just 1 second. I just want to make sure you guys can see the calculation so it makes a little more sense, because I feel like if I'm just explaining it, it might be easy to get a little bit confused. Oh, okay, here we go. All right, it's just taking a second. Okay, let me try typing in here, see if it works. Okay, here we go. So if you guys look in the middle of the whiteboard, you should be able to see it. I hope. But yeah, so calculate the following parameters for this hypothetical computer system. Okay, so how do we do this? So we have where we know we're in octal notation. We know that the IR is equal to 12 bits, PC is equal to 3 octal digits, memory address size equals IR. So I'll go ahead and write out some calculations to try and help make sense of this. So to start, remember, we know that our we have 3 octal digits, right? So that is so thick. Oh my goodness, it's so gross. All right, that's fine. So we have 3 octal digits, and we know that octal is 3 bits because 2 to the power of 3 is equal to 8. So hopefully that makes sense so far. So this tells us the number of bits that we have. And because we know the number of bits that we have and we know we have 3 octal digits, we do 3 times 3 is equal to 9. And this gives us our memory address. And hopefully this makes sense because we have 3 octal digits. Octal digits are 3 bits. That's 9 total bits we need for the specific memory address. And because we know the memory address and we know our IR, the rest is just pretty simple. So we know 12 equals whatever the opcode is minus 9. And because of that, we know that our opcode is just going to equal 3. So we know that we're going to have 3 different opcodes. And because we're calculating our bits, we're going to have 2 to the power of 3. So like we know 12 equals or like 12 equals OP code minus 9 equals 3 opcodes, which basically tells us that we're going to have 2 to the power of 3 opcodes, or 8. And I'm just going to try and remove all this. Hopefully that makes sense. If anybody has any questions about the first part, just go for it. But if not, I'll go ahead and continue. So the next part of the question asks, what is the memory size in bits? Okay, so the memory size is determined by the number of addresses PC can hold. Thank you for moving that. Since the PC is 3 octal digits and each octal digit represents 3 bits, again, we calculate our octal digits bit amount by the number of digits. So again, 3 times 3 is equal to 9. So again, 2 to the power of 3, 3 octal digits, 3 times 3 is 9. So that part's going to be the same. I don't know why Discord whiteboard is so slow. Equal to 9. And we know that to calculate memory size and addresses, we need to calculate 9 bits. So you guys know what I mean when I say calculate 9 bits, right? That means we do 2 to the power of 9. And you're not going to do this in your head. You're going to have a calculator with you. But 2 to the power of 9 in this case is 512. And once we have that, we know that each memory word is 12 bits. Is 12 bits, excuse me. Again, exact same as the IR. So that means that the memory size or that means that the memory size in bits that we're looking for is going to be 512, which is number of bits times 12, which equals, I believe, 6144. And again, this is because we have 12 total, and we got the 512 because we're dealing with 9 bits. So hopefully that makes sense. It's kind of confusing. Just remember to calculate our PC against whatever the notation is, and then we just simply multiply that and then find the bits of that, multiply it against what our IR is, and that's how we get the answer here. So hopefully that part makes sense. It's a little bit confusing. I'm well aware. But if you guys have any questions, I'll do my best to explain. But if not, I can go ahead and continue. So the next two are actually a lot simpler. I'd say that the second one is definitely the hardest one. But 3 and 4 are pretty trivial here. So I'll go ahead and try to give a brief explanation.
Oh,
Yeah, go
wait,
ahead.
we got a question. Someone said, how do you know to multiply the octal digits by 3?
So we know we are multiplying the octal digits by 3 because in the PC it says we're dealing with 3 octal digits. And we also know that our octal digits are 2 to the power of 3 because remember, an octal digit is going to be 8 total values. So that means we're going to have 3 total bits because we're just considering from base 2. So if we have octal notation, that means every single octal digit is 3 bits, and we have 3 total octal digits, so we do 3 times 3. If we had, I don't know, base 16, for example, then we'd have 2 to the power of 4. If we had base 32, then we'd have 2 to the power of 5, etc., etc. But essentially, we know that octal digits are going to have 8 total values, so that tells us we're dealing with 3 bits. And because our PC is 3 total octal digits, we just multiply those against each other to get our value, if that makes sense. And moving on, are there any other questions? I can continue on if you guys need.
They said in this new example, it would be 3 times 4. It should be 12 bits. I don't think.
12 bits
Oh,
for
yeah.
what?
Oh, like in the new example that you did?
Oh,
Okay.
yeah. Because we'd be dealing with hexadecimal. Yeah. So if we had 3 hexadecimal instead, it would be 12, and then we'd be doing 12, 2 to the power of 12, and then would be one or what's it's maybe like 2 to the power of 12 times whatever the IR is, which is 12 bits. It'd be something like this, if that makes sense. But I'll go ahead and continue on. So the memory range is actually super simple. So to do memory range, all you really need to remember is what the base notations are. So if you guys remember, the base notation for octal is 0 to 7 because we only have 8 possible digits we can use. And that means to find our memory range, we just need to take our notation and we need to take the minimum value we could have and the maximum value we could have. So in octal notation, if we have 3 empty octal digits, they're all going to be 0. And at our max with 3 octal digits, they're all filled up to the maximum amount they could be. It would be 7, 7, 7. And if we had base 2, for example, and we had uh, like 0, 0, 0 to 1, 1, 1. This would be if we had 3 base 2 digits. If we had hexadecimal, what is the max value for hexadecimal? Is it E or is it F?
I think that should be F.
Yeah, so if we had 3 digits of hexadecimal, it would be 0, 0, 0 to F, F, F. So this part's super simple. Just remember what the notation is. Remember to keep track of how many total whatever the notation digits is, and then do 0, 0, 0 to whatever the max value of that notation is. That one's pretty simple. If you guys have any questions, go for it. But yeah. And then the total data range. So remember, we're an octal and we have 12 total bits. So this part we're looking at the IR. So we know that from our IR we have 12 bits, and we know that because we're in octal notation, we have 2 to the power of 3, so 3 total bits. So we do 12 divided by 3 equals 4 total octal digits in our data range, which is 0000 to 7777. So for this problem specifically, look at your IR, and make sure you're also looking at whatever the bit amount of your PC value is. And then you just do the division, and that's it. And this is how many octal digits we're going to have in our data range. And then same principle as before, whatever the minimum value is of your notation, and then whatever the maximum value of your notation is. And yeah, that's basically all the problems. So just if you guys, I can write all the answers. Oh, whoops, sorry guys. Let me see if I can grab this.
Is it possible you can grab the other example also? We can paste it there.
Yeah, give me 1 second.
Yes.
I had to yoink the text from it.
Let's see. Hold on.
And then the second question is probably the hardest calculation question you're going to get. And then the third and the fourth, we're going to show you're going to get those too, but those ones are a lot simpler. So here is the second question that we have for you guys. Let me go ahead and drop this first.
The session is being recorded, right? It should be recorded.
I think so. I think there was supposed to be a historian here. But yeah, Manuel, will go ahead and explain this next part. Thanks,
yeah. Here you go. All right, so we're gonna have a So we're gonna have a similar problem, right? But this time, now we're in binary notation, right? So same same problem, right? Same process we're gonna do, right? So in this instance, right, we want to find a number of different opcodes, right? But they already told us that we have 2 opcode digits, right? So right, obviously since it's binary, right? So it's gonna be 2. So I don't know why this is colored, but okay. Right, it'll be 2 to the power of 2, right? So number of digits would just be 4, right? Does anyone have any questions on how I got this or anything? Or anything? I guess no questions. All right, so let's see. The next one we're going to be dealing with is the memory size in bits. So to handle this question, right, first we're going to figure out what the IR is, right? So the IR, right, is this equal to? Let's see, is this equal to? Let me just get the formula. Right, and don't worry, right? If you guys feel overwhelmed by this, right? Like this most, like it's you guys can once you guys have the cheat sheet, right? Most of the formulas should be there, so like you don't be too scared, right? So the IR is just equal to the opcode bits, right? So in this case, it's 2, right, plus the memory address. But the memory address is also equal to the PC, so it's just equal to 3, right? So let's see, right? 2 plus 3, which is just 5, right? We found the IR, right? So if we're doing it, we'll follow by the same notation, right? So it's gonna be 2, right? 2 times 3, right? Times the IR. So we get the memory size in bits should be 40. Has anyone got any questions on where I got this or how I get this? Any questions? Anything at all? Let's see, make sure I did everything right. All right. So then we go to the memory range, right? So which is like the easier one. So in the cheat sheet, right, basically the memory range is just the amount of the bits, right? So here they already gave it to us, right? So it's 3, and since we're in binary, right, the total memory range will be 0, 0, right, and then dash 1, 1, 1. Right. You guys have any questions where I got this or anything? Yeah, I don't see anything here. So, right. And then for the data range, right, same thing. Right. Since we're dealing with, let me check. That's right here. Let's see. Yeah, since the memory word size, right? Since we figured it out, right? It's 5, right? So basically means that the range of values can be stored by those 5 bits, right? So the total data range is just going to be 0, 0, so annoying without a mouse. 0, 0, and then 1, 1, 1, 1, 1. There you go. This is going to be the total data range, right? And if you're wondering how it got this, that's just because this is just the memory word size in bits. Right? Does anyone have any questions? Anything? You guys lost? All right. Then there's this one more free response example that you might see on the exam. So, Victor, is it possible you can paste it here?
Yeah, of course. Let me go ahead and pop this up on here. I'm gonna see if I can zoom in a bit. Uh, give me just 1 second. Okay, this is gonna be a little off. I don't know how to adjust my screen on this whiteboard. It's so weird. Um, okay, so we have our average. So in this problem, you are going to be given your average So you're gonna be it's gonna be average access time, right? L1 memory access time equals 50 ms. L2 memory access time equals 400 ms. And then you're going to be given either the miss ratio or the hit ratio. So calculating the miss ratio and the hit ratio is the easiest thing ever. So basically, you're going to be given one of the miss ratio and the hit ratio. So in this case, we're given that our miss ratio is 20%. So that means that to calculate our hit ratio, all we have to do is just do 100% minus the miss ratio, which is 20%, and then we get 80%. And that's it. Your hit ratio and your miss ratio are always going to add up to 100, and you're always going to get 1. So it's super simple. And then to actually do the calculations, it's literally just algebra. All you have to remember is your hit ratio and your miss ratio are going to add up to 100%. And as long as you remember that, the rest of this is simple. So our formula is hit ratio, which we know is 0.80 times L1 plus L2, which is 50 ms plus 400 plus 400. So, okay, hit ratio time. Oh, sorry, I messed that up completely. Excuse me. Let me go ahead and fix that really quick. So again, yeah, we know our hit ratio is going to be 80, so I'll just write that up top. So HR equals 80. And so to calculate this, we need hit ratio, which is 0.80 times L1, which is 50, plus our miss ratio, which is 0.20 times L1 plus L2, which is 450, times 450, which is going to equal our average access time hit ratio, which I'll just call equals average access time plus miss ratio. Hit ratio plus miss ratio equals 100%. So yeah, so we'll just call this average access time hit ratio. We'll just call it X equals X plus our miss ratio, which again is 0.2. Wait, I'm getting confused here, Manuel. You're gonna have to help me out. It's been a while since I looked at this problem.
No, yeah, it's fine. So let's see. Hold on. Let me get the formula real quick. Let's see. Hold on. I had it somewhere. Where is it? Let me see. Where is the formula? I should have the formula somewhere. Let's see. It should be the hit ratio times that. Yeah. So just you might need to ignore the miss ratio, right? So it should be just equal to that. Is the
Okay.
hit ratio? Yeah. So you don't need the plus miss ratio. You don't need that part. That part you don't. Yeah.
The formula is tripping me out. Okay, so yeah, so we just do the calculations on this. and you'll have a calculator, so I'll just pull mine up and I'll just do it really quick. But 0.8 times 50 is 40, plus 0.20 times 450 is 0.20 times 450 is 90. So 40 plus 90 is equal to 130, which is our final answer. And yeah, that's it. Just remember how to calculate the hit ratio and miss ratio, and then the rest of it's just literally plugging it into the formula, and then you're good. Sorry, I got a little tripped up there. It's the formula's tripping me up. Sorry, guys. But
All right, and then we have one more example for you guys. So, Victor, can you paste it?
yeah, let me pull that up. Give me 1 second.
Yeah.
Sorry about that. All right, I got
All
it
right.
pulled up.
All right, here you go. All right. So in this instance, right, we want to find L2 memory access time, right? But we have everything, right? We have average access time, we have L1 memory access time, hit ratio, right? So let's start, right? So we know, right, if we want to find the miss ratio, right, we can just say, let me see, what we get here, right? It's just one. Let me see. Oops, sorry if this is pretty bad handwriting, but I'm sorry. And what is this equal to 1 minus, minus 0.85, right? Which is just 0.15, right? So we have our miss ratio, right? So now we can actually use the formula, right? So now we know it's just going to be the hit ratio. There's this 0.85. Sorry if that looks like a zero. Any of you guys, I'm sorry about that, right? And the ratio times L1, which is 50. Let's see, times 50. 50 plus, let's see, yeah, plus the miss ratio. Let's see, yeah, plus the miss ratio, which is 0.15, right? Times R L1 plus L2, right? So L1 is 50, but we're going to call L2 X here, right? So X. And this is all equal to our average access time, which is just 117 point, sorry about that, 117.5, right? So, right, if we do like everything here, we should get 42.5, 42.5 plus 7.5 times, plus, sorry, plus 0.15x. I'm so sorry for the person who drew the smiley face. I'm sorry. It's equal to 117, 117.5. Right? So, if we just do standard, what's it called? Standard subtraction, right? We're just going to left with 0.15x, right? When you see, right, 42.5 plus 7.5 is equal to 50, right? So 117.5, right? Minus 50, we're left with 67.5. 67.5. So we divide both sides by 0.15, and we're left with, 0.15. So we're left with L2, right, which is actually basically, right, L2 is equal to 450 milliseconds. That's our answer. Any of you guys can go ahead and ask questions, right? Any questions, comments, or concerns? No. Yes. If there are no questions to be asked.
Okay.
All right.
if you guys are all good, I'm gonna go ahead and just bring the slides back up. And okay. So yeah, that takes us through everything. Do you guys have any other questions for us today? It could be about any other topic, as long as it's just related to OS. If it's something that is kind of new or we didn't cover, we may not be 100% sure, but we'd like to help you the best we can. So yeah, if you guys have anything for us, just go for it. But if not, it's been a pleasure.
Yep. And don't be afraid to message us right through Discord if you guys want like any more like review or if you guys need help overall. Oh, wait, we got one question.
Another parameter question. Could you give an example, or do you have one that you'd like us to go over specifically?
Will you guys be able to post the forking example? Yeah. We'll be able to post the forking example code. Let me see. Hold on. There you go. Let me just
Yeah,
copy paste
just
this.
drop one from the review and we'll go through it real quick.
Let me see. Let me see. Let's see.
Calculate
Oh,
the following parameters. Oh, this one. Okay.
oh, that one. Good. Here's the example forking question. Oh, where you got the 50 plus x in the problem you just did, and because oh, I see 50 point. Oh, yeah. So for where I got 50, right? So the equation, right, is just L1, right? So is this going to be the hit ratio times L1, right? Plus the miss ratio times the average, not the access time, L1 plus L2, right? So X being our L2, which is our unknown, right? But 50 is our L1. So hopefully that should clarify a few things, or would you like to go? Let me see. Let me try to write it down here. Let me see. There you go. That should be the equation. Should be let's see the hit ratio times. Let's see. And so 1 plus the miss ratio. Oops. Oops. L1 plus L2. That is equal to our average access. Average access time. There you go. Right. So here you go. Right. This is the formula you guys will be using. So I did it right. So since our average access time was, yeah. So this should help clarify things. Let's see just in case, right? I'll just write it down here. Plus the MR, which is 15. That's 50 plus O2, which is equal to 1.2. There you go. All right. Nice. See, is there any other questions you guys would like to ask? Nope.
Sorry, I was getting water for a second. Did you cover the parameters question?
Yeah, I finished the parameters. Which one? Oh no, I think you have that one. I can. Can you post it again here?
Yeah, give me just 1 second. I'll
Yeah.
go ahead and pop it in. All right, I'm gonna do this one on the whiteboard. Give me just 1 second to pull it up. There's a lot of stuff on here. Okay, let me pull this up really quick. All right, calculate the following parameters of a hypothetical computer system with these features. A, octal notation, IR equals 12 bits. Hold on, give me just 1 second. All right, IR equals 12 bits. PC equals 3 octal digits. This one looks very similar to the one we just worked on. But all right, I guess we can. All right, calculate the parameters of a hypothetical computer system. All right, what are all the parameters that we need to calculate? I think it's like just everything listed here, right? Okay.
Yeah.
So we need.
No,
Oh,
I think it should be. Hold on, let me see the example. I think the same one we did, but
yeah,
it should be.
we need
Let me
we
see.
need what is it? The OP code, the
Yeah,
mem address. So it's very similar.
yeah, it's the same problem.
Okay. So
Yeah, the number of different opcodes, memory size and bits, memory range and data range. Yeah.
yeah. So what's a good way to? Yeah, this is like pretty much the same, but again, we're dealing with octal notation, and we have PC equals 3 octal digits. So same idea. IR equals OP code plus memory address. So if you guys remembered how we did this earlier, it was IR equals 12, or I'm on the wrong thing. Let me see if I can find my pen. Okay, it is not letting me draw. Sorry. Let me try leaving real quick. Okay, there we go. Where did I post this? Okay. So yeah, if you guys remember, the way we found or we calculated this stuff with IR equals OP code plus memory address earlier. So remember, IR equals 12 bits, or sorry, PC equals 3 octal digits, which is going to be 9 bits total, because remember, octal is 2 to the power of 3, and 9 bits total. So octal is 2 to the power of 3, and then we have 3 total digits. So we just do 3 times 3 equals 9. The memory address is going to be 9. And then we have 12 equals OP code plus, or OP code minus 9. So our OP code is going to be 3. And we don't just take the value 3, we do 2 to the power of 3. And that's basically it for that. So this is our OP code, 2 to the power of 3, which equals 8. So hopefully that part makes sense. IR is equal to 12 bits, which hopefully makes sense. 12 bits is also going to be 4 octal digits. So if I can write this out, but yeah, 12 bits is 4 octal digits. Hopefully that. Oh my goodness, it's hard to draw in here. I don't know why. So 12 bits equals 4 octal. So hopefully that still makes sense. PC equals 3 octal digits, which is going to take us to 9 bits. We just calculated that. The mem word size. So that is going to be 12 bits, which is the size of our IR. So the reason I say 12, or I say 12 bits, is that IR is equal to 12 bits, and we know that our mem word size is set equal to our IR. So this is like the number of bits we have. So we have to do 2 to the power of 12. And the maximum value it's going to be able to hold is 4095. So that's basically it. So this is the max word size we could, or this is the max mem word size we could have. So 4095, because we have 12 bits from our IR, and we just throw that in 2 to the power of 12 to get our value. And again, you're going to be able to calculate this. And the reason I do 4095 instead of 4096 is that you do 4096 minus 1. If I remember right, I think it's because of 0 indexing or something like that. But yeah, you're going to wind up getting 4095. I think that should summarize the parameters pretty good. Besides that, the stuff we covered from before should be pretty similar. Yeah, hopefully that helps. I think that's the way you're supposed to answer that. But yeah, that's how you get the mem word size and all that other stuff.
Yeah, is there any more questions you guys like to ask? Don't be afraid. Don't be afraid and shoot. Shoot your question.
All right, if that's all we got, thank you guys so much for coming. Really appreciate your time. This should be recorded, and you should be able to go over the viewing later on. But yeah, hopefully this helps you guys out. And if there's no other questions, we can go ahead and call it for today. Thanks so much, guys.
Yeah, if you guys have any more questions, right, don't be afraid to reach out to us, and we'll be glad to help you.
All right, have a good rest of your day, guys. Good luck on all your exams and everything.